Okay, darling, call you later. See you. Okay. Boy, boy. Kill me probability of it.
Hi. Hello, everyone. How are you? Welcome on board. Um, First thing first, let me do a sound check. If you are unable to hear me well, please let me know. Yeah, I saw one, two people raise their hand. How is it now? Is it better?
Yes.
Okay, great. All right, let's wait for a few more minutes for the rest to join. All right, I have just shared my screen. I hope you can see the slide. Okay, so I think now it's already 4:07, so I think we need to get started. All right, so this is lecture number 12. So this will be the agenda for today. All right, we are starting a new topic on optoelectronics. All right, so optoelectronics refers to electronic devices that functions based on interaction with light. All right, so the first subtopic that we are going to discuss will be on light-matter interaction. Right, so under this discussion, there are some important points such as wave-particle duality. This is quite famous in quantum mechanics, where light waves can be regarded as particles. Right, so I'm going to review this concept. Now, we will also be looking at how light is measured. What are the units for measuring light? This is important because in optoelectronics, since the electronic devices are interacting with light, we must know how to quantify the amount of light that the devices receive, right? After that, I'll move to discuss basic concepts on light absorption in semiconductor, as well as light emission in semiconductors. Now, the absorption and emission were already discussed in part 1. So what we're going to do is that we're going to go a bit more in depth to introduce more new materials, right? Such as under absorption, we are going to look at Lambert's law, which quantify the absorption of light in semiconductors. Under emission, we are going to talk about spontaneous versus stimulated emission. Although we do not have time to go in depth into stimulated emission, right? The discussion is just to let you be aware that emission can be classified as spontaneous or stimulated. And then I'll end the discussion with a brief mention on reflection and refraction. I think most of you guys would know what these are by now. All right, why these are important? Because light interacts with semiconductors, and as a result of the change in
Oh shit, bro! I was in another one.
as a result of the change in medium, right? So part of the light will be reflected, and the light that is transmitted will involve a change in direction, which can be important during the operation of the optoelectronic device. Now, after this discussion, we're going to look at 2 application examples of PN junction, which involve light. The first one is light emitting diode. Some of you who did the lab 3 yesterday, you already, experimented with this, right? Where you measure the light emitting out of LED under different biasing conditions. Okay, so hopefully that will give you a better background on how to deal with some of the questions in your lab report. Then this topic will end with a discussion of photodetector. A photodetector device does exactly the opposite, right, to what an LED does. Basically, an LED emits light, a photodetector detects light. It does not emit light, right? It converts light into electrical energy. Whereas in LED, it converts electrical energy into light. Okay, so this will be the layout for this topic. Now, the discussion will span 2 lectures, 12 and 13. Okay, so let me get started. Okay. Now, what are optoelectronic devices? Optoelectronic devices are semiconductor devices, right, which operates based on an interaction with light. Now, there are 2 very important examples. The first one is the light emitting diode. Now, the diagram on the left shows you the different types of light emitting diodes. Right, I think most of you are aware how an LED looks like by now. It normally comes in a hemispherical shape like this. There's a reason to do that, which you will be able to understand later on. Why people shape an LED like this. And by the way, the this object, this hemisphere that you see here is not the LED itself. All right, it's actually a plastic compound enclosing the LED. The LED is actually somewhere here. If you look at this particular LED, the PN junction, the light emitting diode is actually somewhere here. Okay, all right. Why must it be enclosed in a hemisphere like this? There's a good reason for that. So we will go into that later on. Now, the other important example on optoelectronics would be photodetectors. So the figure on the right shows you the photodetectors, some common examples. All right. Typically, you will see a glass window here because a photodetector is a device that detects light. So there must be a way for light to get into the semiconductor device. Okay, so it is normally enclosed in a metal casing like this with a glass window here for light to penetrate and reach the semiconductor device. Okay, so this is an example of a photodetector. So besides LED and photodetector, there are two other very common examples. The third one would be solar cell. I'm sure most of you have heard of solar cells. Okay, a solar cell is a device that generates electricity out of sunlight. It is actually a type of a photodetector, if you may put it. All right, so it essentially converts light into electrical energy. Now, another very common example is laser. I'm sure you know what a laser is. By the way, the word laser is actually not a formal English word, right? It's not a proper English word. It's actually an acronym, which stands for light amplification by stimulated emission of radiation. We will not be discussing laser. Laser is not in your syllabus. But the way it operates is quite similar to LED. But there are some important differences which I can highlight later on if we have time. We should have time. So after discussing LED and photodetectors, if we have time, then we can talk briefly about lasers. But laser is not inside your syllabus, so it's not examinable. All right, now optoelectronic devices are semiconductor devices designed to interact with part of the electromagnetic spectrum, typically the visible spectrum and the infrared as well as the UV. Okay, so what an optoelectronic device does is that it simply either convert electricity into light or it convert light into electricity, one of these two functions. Okay, so devices that convert light into electricity are photodetectors and solar cell, and devices that convert electricity into light are lasers and LEDs. Okay. Now, this is a brief introduction on the electromagnetic spectrum. I think most of you are familiar with the electromagnetic spectrum. I believe it has been covered in your physics course. Now, the electromagnetic spectrum is a very broad spectrum. All right, if you describe the electromagnetic spectrum in terms of wavelength, the wavelength in meters, right, can range from 10 to the power 3 meters, which is essentially a few kilometers, to 10 to the power minus 12 meters, which is picometer, 1,000 times smaller than nanometer. Okay, so it's a very broad range of wavelengths, and the objects that you see here typically are meant to give you an idea of how long certain wavelength is and how short certain wavelengths can be. Okay, so if you look at the left side of the spectrum, all right, the electromagnetic waves could have wavelengths as big as a soccer field or even a house like this. All right, so if you look at the right side of the spectrum, all right, the electromagnetic waves have wavelengths on the order of the size of molecules or atoms, or even smaller, subatomic particles. Okay. Now, very long wavelength electromagnetic waves, a good example is radio waves, right? Radio waves are signals that radio station emits and your radio picks up. For example, is some of the radio stations like 91.3, all right, they emit radio waves having wavelength on the order of kilometers. Okay. Now, after radio waves will be microwave, right? Having wavelength around 0.1 meter to about 10 to the power minus 4 meters, right? So this range belongs to microwaves. Then after that will be the visible spectrum, but before that will be the infrared spectrum, which the human eye cannot see, right? And if you go towards a wavelength of about 700 nanometer, right, you will start to see red light. Red light is around 700 nanometer. And if you go further down, you will reach the blue light, all right, or the violet light. All right, the violet has wavelength of about 400 nanometer. Now beyond violet, you get ultraviolet. That means below 400 nanometer, you get UV light, ultraviolet light. Okay, which again the human eye cannot see. Okay, and going below that again, you have X-rays, soft X-rays, and hard X-rays, which of course are invisible to the human eye. Gamma rays as well. Okay, so this is the electromagnetic spectrum. It's a very, very huge spectrum, very broad spectrum. And for optoelectronic devices, we are concerned with the visible range as well as its neighbors, right? The infrared and the ultraviolet. Okay. Now, light in the visible range is a form of electromagnetic wave, right? Which can be described by Maxwell equations. In fact, all electromagnetic waves can be described by Maxwell equations. Now, Maxwell equation is a set of very important equations that lay the foundation for classical electromagnetics. Okay, so these are the four Maxwell equations. They are expressed in differential form. This inverted triangle, I'm not too sure if you are familiar with this. This inverted triangle is called the divergence operator. Now, if you look at only one dimension, for example, along the x direction, this divergence operator simplifies to a differential operator, which is d over dx. Okay, all right. Okay, maybe I will show you an alternative expression for the Maxwell equation. All right. Well, you do not have this slide, so don't worry. I mean, this is not that important, but just to let you be aware that the Maxwell equations can also be described in integral form, which are easier to understand than the differential form. So if you look at the first equation, right, in the integral form, it looks like this. I think some of you may recall that you actually have seen this before. All right, the E here stands for electric field. The S here stands for the surface, and ds represents a surface vector. And this dot here represents the dot product of the electric field vector and the surface vector. Okay, I think now you recall where you saw this previously. This is actually Gauss's law, right? The first Maxwell equation is actually Gauss's law for electricity. In other words, if I take the dot product of the electric field vector with the surface vector and then sum it up over the entire Gaussian surface, on the right, I will get the charge enclosed Q divided by the permittivity of the medium. I mean, if you assume vacuum, then is the absolute permittivity or the permittivity of vacuum, epsilon naught. Okay, so the first Maxwell equation is actually Gauss's law, which you saw before. Okay, now the second Maxwell equation is actually Gauss' law applied on magnetism. Now, if you apply Gauss' law to magnetism, in other words, magnetic field, basically the B here stands for magnetic field. If you do the same, take the dot product of the magnetic field and the surface vector and perform an integration over the entire surface, the result is always 0. Okay? The reason is because magnets do not exist as a monopole, right? A magnet always exists as a dipole. In other words, it always has a north and a south pole. Okay, so in other words, magnetic field lines always begin at the north pole and you end at the south pole. So if you draw a Gaussian surface that encloses the magnet, the result for the integral here will always be 0 because you have a magnetic field coming out of the magnet and as well as returning to the magnet. Okay, so the sum is 0. Okay, now the third equation is actually the Faraday law of induction. Well, essentially it says that changing magnetic field can lead to an electric field, right? Faraday's law of induction. And the last equation is actually Ampere's law, which says that a magnetic field can exist as a result of current flow or the presence of an electric field. Okay, very often scientists jokingly say that Maxwell actually did nothing but he grouped some of the equations from other famous scientists together and call them his own. But well, nevertheless, the Maxwell equation actually formed the foundation for classical electromagnetics. So it's still a very important set of equations. Okay, all right, so this is a very brief introduction to Maxwell equation. We are not going to use them in our discussion for LED and photodetectors. Okay. Now, the next important concept I want to review is the duality nature of light. In the sense that in quantum mechanics, light can be considered as particles or packets of energy called photons. I think this concept should be familiar to most of you by now. Okay, now, light at the same time can be regarded as waves, right? So that gives this name the particle wave duality nature of light. So when do we regard light as particles and when do we regard light as waves? I'll come to this later on. Okay. Now the particle theory for light is described by a very famous theory called Planck's quantum theory. Right. Essentially, it states that the energy of a photon can be related to its frequency f according to this equation, where essentially E is proportional to f, and the constant of proportionality is called the Planck's constant. Okay, which has a value of 6.626 times 10 to the power minus 34 joule second. This is the standard SI unit for Planck constant. All right, of course, frequency can be expressed in terms of the speed of light and the wavelength. Right, it's c over lambda, or lambda times frequency gives you the speed of light. I think you should be able to know or understand this by now. Okay, so wavelength is given in meters and speed of light is given in meter per second. So just take note of the unit. Okay, so this is a picture of the great Max Planck, right? The great scientist that postulated this quantum theory of light. Okay. Now this equation E equals to HF can be expressed in a more convenient form, right? After you substitute the values for H and the value for the speed of light, right? And if you manipulate the units such that the energy is expressed in terms of EV and the wavelength is expressed in terms of nanometer, then the value for the numerator here will be 1240. Okay, now this serves as a very convenient expression. All you need to remember is 1240. Okay, so if you have lambda, if you have wavelength in terms of nanometer, for example, 1000 nanometer, you can immediately know the photon energy. All you need to do is just to take 1240 divided by 1000 expressed in nanometer. So the photon energy will be 1.24 EV. Okay, all right. So you might want to keep this in mind. It's a very convenient expression to use. Now, take note that the wave nature and the particle nature of light, they are complementary. In other words, you cannot interpret a particular phenomenon, all right, using both behaviors. There will be some contradictions, all right? So that's what is meant by complementary. Only one will work, okay, under certain situations, okay? So when one deals with light-matter interaction, such as the interaction between light and semiconductor, normally the particle theory will be very useful. Okay, all right. Now, we have already seen some examples, right? For example, light emission in the form of photons or light absorption in the form of photons. Okay, all right. So the particle theory is well supported by experimental evidence from semiconductors. All right. If you remember, right, if you shine light on a semiconductor, only light of certain wavelength can trigger electron hole pair generation. Right. What else? If you shine light below a certain wavelength, below the cutoff wavelength, then no electron hole pair generation will happen. So this behavior actually gives a very solid evidence or proof for the quantum nature of light, or the quantized energy of light in the form of energy packets. Okay. Now, on the other hand, if you deal with light and light interaction, such as the interference between two light waves, then the wave theory is more consistent. Right? Well, particles, it's hard to imagine how particles can interfere or constructively or destructively. Okay, so when you want to describe light to light interaction, then the wave theory is more convenient and consistent. Okay, so keep that in mind. Now, the next thing I want to discuss is on light measurement. Now, since we are going to deal with devices that interact with light, it is important for us to know how light can be measured. What are the units commonly used to describe the measurement of light? Now, the units can be classified into two categories. The first is called radiometric units. Okay, now radiometric units are very objective. In other words, if everybody describes a certain amount of light in terms of a radiometric unit, then it refers to the same amount of energy or same amount of power, etc. Okay, so it's a very objective unit. All right, and a good example of radiometric unit is watts, right, or joule per second. Okay, so another example would be intensity. Intensity is another example of radiometric unit. All right, intensity would be watt per unit area. Okay. Now, the other category is the photometric unit. Now, photometric unit is more subjective. Actually, it's based on the sensation of brightness as perceived by the human eye. Okay. I will discuss this in more detail soon. Now, a very common unit, a very common photometric unit is lumen. Lumen. Another common unit for those of you who did the lab yesterday, another common photometric unit is lux, Lux. Okay. Now, how are the two linked? In other words, how is a radiometric unit such as watt linked to a photometric unit such as lumen? Okay, they are linked together by this curve called the standard luminosity curve. All right, an example is given on the next slide. So I'll go to the next slide first. So this is the standard luminosity curve. All right, so on the vertical axis, it gives you the relative efficiency of the human eye in perceiving light of a given energy. Okay, so on the horizontal axis, you have the wavelength. So what does this curve mean? Okay, essentially the curve is defined such that at a wavelength of 555 nanometer, 1 watt of light energy at this wavelength is defined as 680 lumens. This is by definition. Okay, so below 555, if you go to 500 nanometer, all right. So what does this 0.4 mean at 500 nanometer? Okay, so 0.4 means that 1 watt of light energy is the same amount of light energy in terms of absolute energy. 1 watt of light energy at 500 nanometer would be equivalent to 0.4 times 680 lumens. So if you take 0.4 times 680 lumens, the answer would be 272 lumens. Now, why is it lower? Remember, lumen is used to measure the sensation of brightness as perceived by the human eye. It turns out that human eye is most sensitive to this wavelength, 555 nanometer, which correspond to green light. Green light has a wavelength of 550 nanometer. Okay, so that's how the definition is fixed, because the human eye is most sensitive to this particular wavelength. Now, below this wavelength, you go into the blue and the ultraviolet region. All right, so the human eye is less sensitive to, for example, blue light at the same amount of energy. Right, 1 watt of blue light will appear dimmer to the human eye than 1 watt of green light. Okay, so this is the meaning of the standard luminosity curve. Now, similarly, if you move above 555 nanometer, if you go to, like, for example, 600 to 700 nanometer, you are going towards the red side of the visible spectrum. So similarly, the human eye is less sensitive to red light of an equivalent amount of energy. All right, it appears dimmer than green light of the same amount of energy. Okay, so this is how the two units are linked together, radiometric and photometric units. Okay. Okay, so that is the definition for the lumen. Okay, this is how it is defined, right? 1 watt of light energy at 555 nanometer is equal to 680 lumen by definition. Okay, right. So the first bullet describes what I have just mentioned. So this is how we use the curve. All right. So for a given wavelength, if you consider 1 watt of energy, of light energy at that wavelength, you just take the efficiency multiplied by the definition, 680 lumens. That will give you the number of lumens at that particular wavelength for the same amount of light energy as perceived by the human eye. That is the brightness as perceived by the human eye. Okay. Now, another commonly used radiometric unit is intensity. Yeah, I just mentioned that a moment ago, or called irradiance or intensity, which is measured in watt per meter square. Okay, so it's basically the amount of power of light power delivered to per unit area of the surface. Okay, right. The corresponding photometric unit, right, is actually illuminance. Okay, which is expressed as lumens per meter square. Now the table below is meant to give you some idea on the lumen scale. I mean the how bright a certain number of lumen per unit area is. Okay, so if you consider sunlight on a very bright day, it's typically around 100,000 lumens per meter square. All right, if you look into the interior, right, like inside your house, in the classroom, in the LT, for example, it's typically around 200 to 400 lumen per meter square. It's much dimmer. All right, fluorescent lighting is widely used in the interior of buildings and so on. Okay. Now, if you talk about moonlight, of course, it's much dimmer. It's only about 0.2 lumen per meter square. Okay, so you can hardly see anything under the moonlight. Okay, so that is a very brief discussion on the measurement units for light, which is important. Okay. The next concept I want to review is related to absorption and recombination. There will be quite a bit to discuss here. Okay, but some of them you already know from part 1, right? So for example, what does absorption of photon mean in terms of semiconductors or in terms of quantized energy level E1 and E2? So let's consider a much simpler example where this particular system has only 2 discrete energy levels, E1 and E2 and nothing else. In other words, there are only 2 energy levels here, no energy levels elsewhere. Okay. Now, absorption simply means that an electron can be promoted from energy level 1 to energy level 2 if it absorbs a photon having an energy exactly equal to the difference between E2 and E1. All right. For photon energy other than E2 minus E1, no absorption can happen. Okay. Now, emission of light is the reverse process. In other words, emission happens when an electron situated at a higher energy level falls to a lower energy level E1. Okay, so the difference in energy E2 minus E1 must be conserved, and it can be emitted in the form of light if certain condition is met. All right. So that's the basic concept behind absorption and radiative recombination. Now, recombination that result in the emission of light is called radiative recombination. Okay. Now, this slide describes what I've just mentioned. Very strictly, absorption can only happen if the photon energy is exactly equal to E2 minus E1. Any other values, no absorption can happen. Okay. Now, the frequency of the light that correspond to this energy difference can be easily computed using the E equals to HF equation that you saw earlier. Okay, all right. So this is a very simple review of what you already know. Now, just now I mentioned about the experimental evidence in support of the particle nature of light. This is a similar evidence. I think in physics you might have discussed this before. Essentially, if you take an element like the hydrogen, for example, now in the ground state, in other words, in an unexcited state, the only electron in the atom is situated at the n equals to 1 level. Okay. But of course, the hydrogen atom can be excited in the sense that we can shine light onto the atom, and the light energy can promote this electron to higher energy levels such as 2, 3, 4, and 5. Okay, so for example, if you promote the electron to level 2, okay, here, all right, and if the electron falls back to level 1, it will emit this amount of energy. Okay. On the other hand, if the electron is promoted to level 3, if it falls back to the same first level here, then it obviously emits a larger amount of energy. So for transition down to n equals to 1 level, you will have a series of discrete wavelengths of light emitting from the hydrogen atom. Okay, so this series of wavelength is called the Lehman wavelength, the Lehman series. Okay, not the Lehman brothers, but is another scientist. Okay. Now, on the other hand, if the transition of the electron goes from higher energy level to n equals to 2 level, then you'll get another series of wavelength appearing, right? Or the light having another series of wavelength coming out from the hydrogen atom, and this is called the Balmer series. All right, the Pachin series is for transition to n equals to 3. All right, from higher level down to n equals to 3. So this experimental evidence of discrete values of wavelength coming from excited atom is another very concrete proof for the quantized nature of energy, or the quantum theory of energy, of light. Okay. Now, in semiconductors, instead of 2 discrete energy levels, we now know that they are energy bands, right? And the 2 most important energy bands are the conduction band and the valence band. Because why are these 2 the most important? Because the conduction band is partially filled, all right? Most of the time it is empty, and the valence band is partially empty. Most of the time it is filled. Okay, now there are other energy bands besides the conduction and valence band, but those energy bands are not relevant because they are always fully filled. In other words, electrons in those energy bands do not participate in electrical conduction at all. All right, so that's why in a semiconductor, the conduction and the valence bands are the 2 most important bands. Okay, now because a conduction band, before that, okay, just to show you the Lehman series, the Balmer series, and the Pachin series. Okay, so this is what I mean by a series of discrete wavelengths appearing. All right, if you measure the frequency of the light coming out of excited hydrogen atom. All right, so the Lehman series is actually somewhere in the range of the ultraviolet. All right, the Balmer is actually in the visible light range, and the Pachin is actually in infrared. Okay. Now, in semiconductors, we don't deal with discrete energy levels. We deal with energy bands, right? An energy band such as the conduction band is simply a series of very closely spaced energy levels, right? So is the valence band. Okay, so absorption can result in the excitation of a valence band electron to the conduction band. And because we're dealing with a series of energy levels, so strictly more than 1 photon energy can result in electron hole pair generation. Okay. Of course, if the photon energy is less than the band gap, then no electron hole pair generation can happen, unless there are defect states situated within the band gap. Then it might be possible to have absorption as well. Okay. Now, because only photon with energy bigger than the band gap can be absorbed, right? this explains actually why some semiconductors are transparent. A very good example is diamond. Diamond is actually a semiconductor with a relatively large band gap of 5.5 eV. Okay. So as you know, if you consider the visible spectrum of the electromagnetic spectrum, the visible range, if you convert the wavelength into photon energy, you see that for the entire visible range, the photon energy is actually less than 5.5 eV. All right, so visible light can actually pass through diamond without being absorbed. That's why diamond appears as transparent. Okay. Now, absorption in semiconductors result in the creation of electron hole pairs. You know this very well. And because absorption results in the creation of mobile charges, electrons and holes are relatively free carriers inside a semiconductor, so they can be moved in a particular direction, and the movement will constitute a current flow. Okay, right? You have restudied this, right? Drift current is one of the two basic transport mechanism, carrier transport mechanism in a semiconductor. And in fact, light absorption is actually the basis of the photodetector. We'll come to that later on. Okay. Now, from here onwards, the concept is new, right? I think you didn't study this before in part 1. Now, what I'm going to do now is to introduce this very important law called Lambert's law. It's related to the absorption of light in a piece of semiconductor. So let's consider light of an initial intensity I0 shining on a piece of semiconductor. So if the photon energy is larger than the band gap, it is possible for the light to be absorbed, and absorption will result in an exponentially decaying intensity as you go further into the semiconductor. Okay, so I0 here is the initial intensity. I as a function of x, x refers to distance into the semiconductor. All right, so the intensity of light after it travels a certain distance into the semiconductor will have decayed to a much lower value, all right, described by I0 times an exponential term e to the power minus alpha x. And alpha is called the absorption coefficient. All right, it is a measure of how strongly the light is absorbed. Now, the Lambert's law can be derived based on a very simple argument, which I will present to you on the next slide. So let's say this is a piece of semiconductor we are interested in. So light of initial intensity is coming in on one side here. Assuming the photon energy is bigger than the band gap, so light will be absorbed, or the photons will be absorbed. Now, Lambert's law simply states that the decrease in the light intensity at a particular distance x inside the semiconductor, right, is directly proportional to the amount of light intensity at that particular position. That is the basis of Lambert's law. Okay, if you consider a small element here, bounded by these two red lines here, okay, so if the light has an intensity Ix on the left side, after traveling a distance of delta x, it will have a different intensity, okay? And the change in intensity due to absorption within this small element is proportional to the intensity at the particular position times the distance that the light travels. Okay, so that is the basis of Lambert's law. If you bring delta x to the left, to the denominator on the left side, and you take the limit of delta x tends to 0, on the left, you will get the first order differential di over dx. In other words, the rate of decrease of light intensity at a particular point x inside the semiconductor is proportional to the intensity at that particular location. And the constant of proportionality is alpha, which is described as the absorption coefficient. Now, there's a negative sign here to indicate that this differential is negative In other words, the intensity of the light is decreasing with distance into the semiconductor. Now, this gives us a first order differential equation which can be easily solved by the technique of variable separation. Okay, so you separate the two variables, you bring this term involving the I, the intensity, to the left and the dx to the right and integrate both sides. Now, you have seen many examples of this earlier on. So you should be able to solve this first order differential equation using variable separation. Now, after you solve it, you will need to determine the constant of integration, and that can be done using the boundary condition on the left side here, where typically the intensity of the light is known beforehand. Okay, so when x is equal to 0, the intensity of the light is I naught, and from there the constant of integration can be determined, and this is the final solution, which is Lambert's law. All right. Okay.
Sorry,
Yes?
in the first line of equation, is that symbol alpha or directly proportional?
Okay, the first line here, right? This symbol here is the symbol for direct proportionality. This is not alpha. All right, this is alpha. They are not the same. Okay.
But I don't get the jump from the ix plus delta x minus ix is directly proportional to that. So how does that come about?
That is the basis of Lambert's law. In other words, if you consider this very small element, all right, a very, very narrow strip of semiconductor here, okay, now the change in the light intensity from the left to the right over a distance of delta x, okay, is assumed to be directly proportional. All right, this delta I, the change in the light intensity, is assumed to be directly proportional to the light absorbed within this small element. Okay, right?
Oh, okay, I see. Okay. Thank you, Prof.
All right, so there's Lambert's law. We can use it later on when we deal with photodetectors. Okay. Now, a point on alpha, right? Alpha is called the absorption coefficient. Okay, it is actually a measure of the absorption strength of a semiconductor. Now, when alpha is large, basically the light intensity decays faster as you go into the semiconductor. On the other hand, if alpha is small, for example, alpha 2 here is smaller than alpha 1, so the light intensity decays more slowly into the semiconductor. In other words, light absorption happens at a slower rate when alpha 2 is smaller than alpha 1. Right? Alpha 1 is the larger, so the light absorption happens at a faster rate as the light travels into the semiconductor. All right. So alpha is given this name called the absorption coefficient. It's a measure of how strongly the light is absorbed by the semiconductor, and is a basic property of a semiconductor. Okay. Now, so different semiconductors have different alpha values. So the next graph that you see here, all right, gives you the values of alpha for common semiconductors such as silicon, germanium. Is that germanium? Yep, germanium is here. Gallium arsenide, and as well as other 3,5 compound semiconductor. Okay. Now, if you take silicon, for example, right, this blue line represents how alpha will vary with the wavelength of the light shining on silicon. Now, if the wavelength is too long, above about 1.1 micrometer, okay, right, you see that alpha drops very quickly to a very small value, almost 0. Okay, this is a logarithmic scale, right? So it drops very quickly towards 0 for long wavelength. The reason is very simple. Okay, because when the wavelength gets too long, the photon energy gets too small. When the photon energy gets smaller than the band gap of silicon, then no absorption can happen. So alpha is 0, right? Now, alpha starts to increase when the wavelength goes below about 1.1 micrometer. Okay, that is because at this particular wavelength, the photon energy just become equal to the band gap of silicon. And of course, when you reduce the wavelength further, the photon energy increases further. And of course, that would enhance the light absorption inside silicon. Okay, now basically what this picture is trying to tell us is that alpha is a function of wavelength. There's a cutoff wavelength above which no absorption happens. Below the cutoff wavelength, absorption can happen. Not only absorption can happen, but alpha continuously increases with the decrease in the wavelength. And this behavior is seen in other semiconductors as well. Okay. All right, so the next thing I want to discuss is for us to try to understand why the alpha increase with a decrease in the wavelength. All right, why does alpha increase with a decrease in the wavelength? Now, there are two possible explanations. In both explanations, it is important to keep in mind that for shorter and shorter wavelength, the photon energy gets larger and larger, and it becomes higher and higher compared to the band gap energy. Okay, all right. So essentially, when alpha goes up, it simply means that light of a higher photon energy can be more strongly absorbed by the semiconductor. So why is that so? Okay. Now, there are two possible explanations. The first explanation relates to the number of electrons in the valence band and the number of energy states in the conduction band, right? Remember, in the earlier discussion, you were told that the available density of states in the conduction or in the valence band is described by this density of state function. Okay, if you recall, the density of state function is proportional to square root of E minus EC. For example, if you consider the conduction band, the density of states is proportional to square root of E minus EC. Now, what that means is that if you go above EC, right, if you go higher and higher in terms of energy above EC, there are more and more density of states, or the density of state increases. Okay, all right, there are more and more energy states, or the density of state increases, okay, above EC. Now, what that means is that with more available energy states, more electrons can be found at higher energy levels above EC. Now, similarly, if you consider the valence band, the density of states in the valence band is proportional to square root of E minus EV. So if you go down into the valence band, the density of state increases. In other words, there are more and more energy states as you go deeper into the valence band. Okay, so with this in mind, so it simply means that if you go deeper into the valence band, you find more and more valence electrons. If you go higher into the conduction band, you find more and more empty energy states. All right. So why does light having a photon energy much larger than the band gap, why is it more easily absorbed? Because a very energetic photon having a large energy, much larger than the band gap, can interact with electrons deep inside the valence band, and you find many of these electrons. All right. Remember, the number of electrons increases as you go deeper into the valence band. So the chance of the photon being absorbed is higher. Okay, right? Because there are many electrons that the photon can interact with, so the chance of it being absorbed is greater. Okay, now at the same time, since energetic photons can promote electrons deeper into the conduction band, since there are so many energy states, available to accommodate these electrons deeper into the conduction band, so absorption becomes possible. Okay, right? Because now remember, for an electron transiting from a lower energy level to a higher energy level, there must be available energy states at the higher energy level to accommodate the electrons. Okay, so since there are many available energy states deeper into the conduction band, so they can accommodate the many electrons that you find deeper into the valence band. So that's the first explanation why alpha increases with a decrease in the wavelength or an increase in the photon energy. Okay, which is described here. All right. Now the second explanation relates to the different number of transition possible involving photon of higher energy. So, okay, what do I mean by that? So if you consider a photon having energy just equal to the band gap, then the number of possible transition is very limited. In other words, this photon can only excite electrons near the top of the valence band to the bottom of the conduction band. Okay, so the number of transition possible is very limited. Now, on the other hand, if you consider a photon of much larger energy, right, this photon can excite electrons deeper in the valence band to the conduction band edge, or electrons higher near the top of the valence band, deeper into the conduction band, or an electron somewhere in the middle of the valence band to a energy state somewhere in the middle of the conduction band. So what I'm trying to say here is that the number of possible transition, right, increases with the photon energy, or more energetic photons can excite electrons in many different ways. All right, so that increases the chance of the electron being absorbed by the semiconductor. Okay, all right, so these are the two possible explanations why alpha can increase with photon energy. Now this trend of alpha increasing with photon energy is important in photodetector operation. Remember, if you consider the visible light, it has different wavelengths. For example, blue light has a wavelength of around 400 nanometer, and then red light has a wavelength of around 700 nanometer. In other words, the photon energy of blue light is approximately double that of red light. Okay, in other words, a blue light has more energetic photon. So the absorption coefficient for blue light is higher than that of red light. And that can cause problems in the design of the photodetector. Or in other words, blue light tend to be more easily absorbed near the surface of the semiconductor, but red light can penetrate deeper into the semiconductor. Right, so this difference in the absorption can cause design issues in the photodetector. We will talk about this later on. Okay, so absorption applies to photodetector. Now, before going to emission. So let me just digress a bit and talk about reflection and refraction. Now this will be very brief because I think you know what these are by now. So what is reflection? Reflection simply refers to the bouncing back of the light ray when it strikes a medium of a higher density. Right. For example, when light travels through vacuum or through air and it strikes semiconductor material here at the surface here, this light ray can bounce back. And the angle of reflection is equal to the angle of incidence, right? The law of reflection states that. Okay. Now, there are some terminologies which might be useful to know. One is called the specular reflection. In other words, reflection happening at a very smooth surface where the light rays are reflected very consistently in the same direction like this. Now, The other type of reflection is called diffuse reflection, which typically happens on the rough surface. Right, so on the rough surface, when the light shines on the rough surface, you get rays reflecting in all different directions due to how the light actually strikes the surface, the rough surface. Because the angle of incidence can be very different at different parts of the surface, if the surface is rough like this. Okay, so you get reflection coming from, coming in many different directions. Okay, right. Now the reflection is a very important consideration in the operation of the optoelectronic device because it limits the amount of light transmitted to the semiconductor. Now imagine if this gray region here represents a semiconductor, then if light tries to enter the semiconductor, some of it will bounce back. So that limits the amount of light that actually gets transmitted into the semiconductor. Right, so that is reflection. Now, refraction is a totally different thing. Refraction simply means a change in the direction of the light ray when it travels from one medium to another medium. Okay. Now, if you take the example of a light traveling from air or vacuum and it strikes a denser material here, for example, water or semiconductor, right? Because the semiconductor or water, which is denser, typically have higher refractive index. So basically what happened is that the angle of refraction in this case will be smaller than the angle of incidence. Okay, right? So this means that the light direction has changed. Okay, or the bending of light has happened due to refraction. Now this is a good example of refraction. You can actually see this happening if you take a prism block like this, and then you on one end you shine a torch or a laser beam. You can see the bending of the laser beam as it travels through the glass material. Okay. Now, why is refraction important? Refraction is important because it limits the amount of light that can escape from the semiconductor into air or into vacuum. And this consideration is important for LED, light emitting device. Right? In the LED, the light is generated inside the semiconductor. And light will undergo reflection as well as refraction when it tries to pass from semiconductor into air or into vacuum. Okay, so refraction limits the amount of light that can escape from the semiconductor into the air. This point will become clearer later on when we discuss in detail the operation of the LED. All right. And also, I think this point you are also familiar. For refraction, the angle of incidence can be related to the angle of refraction through Snell's law, SNELL. Right, we will use this later on when we quantify the amount of light that can escape from the semiconductor into air. Okay, a bit more on reflection. I'm not sure if you already know this. Reflection can be quantified by this parameter called reflectivity, which is defined like this: N1 minus N2 over N1 plus N2. N1 is the refractive index of medium 1. N2 is a refractive index of medium 2. Okay, so R is a number always less than 1, but greater than 0. Okay, right? So basically what it means is that when light strikes the interface between two different media, part of it will always bounce back, and the fraction of light that bounces back is quantified by this parameter called reflectivity. Okay, reflection actually has a more proper term. It's actually called Fresnel reflection, right? Named after this scientist. I think he's a French scientist. Okay, right. So now, reflection can be put to good use actually in a semiconductor device such as LED. If you look at this picture, what you see is a PN junction. Later on, you will learn LED, and LED is none other than just a forward bias PN junction. Okay, so as you know, under forward bias, you get electron hole injection across the PN junction, and recombination of the excess carriers will happen. And if the PN junction is built using a direct bandgap semiconductor, then emission of light can happen. So while reflection limits the amount of light transmitted from semiconductor to air, it can be put to good use by collecting light that scatters in the other direction that could not escape into air. For example, at the bottom of the N region here, we can coat it with a very shiny metal material, right, to form a reflective coating here. So when the light hits the bottom, it can be reflected back and it might have a chance to escape into the air to become a useful light output. Without the reflective coating, then this photon will not be able to escape into the air. The chance of it is that it most likely will be reabsorbed by the semiconductor. Okay, right? Now, well, another parameter is called the transmittivity. Transmittivity is just a complementary of reflectivity. It simply describes the fraction of light that is transmitted onwards from one medium to the next medium. Okay, so T, transmittivity, is simply 1 minus R, reflectivity. So it's quite easy to understand. So if you consider two different media here, right? So the fraction of light that get transmitted will be R times the original intensity. And the fraction of light that actually get reflected. So the fraction of light that actually get transmitted is actually T times I naught, where T is simply 1 minus R, right? Okay, let's do one word example before we go for the break. All right, so now, this is just to let you have a feel of the amount of light that can be transmitted or reflected for common semiconductors such as silicon. Okay, you can repeat this exercise for germanium, right? So if we consider light of two different photon energy, 1.2 eV, which corresponds to the infrared region of the electromagnetic spectrum, and 2 eV, which correspond to the red part of the visible spectrum, having intensity 100 milliwatt per meter square, incident normally from air onto a silicon wafer. All right, so I asked to calculate the reflected intensity. In other words, the amount of light that bounces back. The intensity absorbed in silicon upon traveling the first 20 micrometer, and the intensity transmitted after traveling through the entire silicon wafer of thickness 300 micrometer. Okay, so to do the calculation, some basic parameters must be known. One of them would be the refractive index of silicon, and the other would be the absorption coefficient of silicon. Now, the refractive index varies with the wavelength of the photon energy. So the refractive index is 3.56 for the photon energy of 1.2 eV, and is higher at 3.91 for the more energetic photon at 2 eV. Now, the alpha, the absorption coefficient, is also very different at the 2 photon energy. It's much lower for the less energetic photon as compared to the more energetic photon. Okay. So how to do the calculation? There are some considerations. So the first thing that you need to consider would be reflection at the surface between air and semiconductor. Okay, at the interface between air and semiconductor. So we can calculate the reflectivity for a photon of 1.2 eV, right? you can calculate the reflectivity. So for silicon, right, which has a refractive index typically around 3.5 to 3.9. All right, and assuming that the refractive index for air is 1, the reflectivity is typically around 30%. So 1/3 of the light will bounce back. It will not get transmitted into, about 1/3 of the light will bounce back. It will not get transmitted into silicon. And this can be an important consideration for photodetector application, because in photodetector device, we rely on the semiconductor absorbing the light energy and converting the light energy into electrical energy. So if reflection limits the amount of light transmitted into the semiconductor, so that will impact the amount of electrical energy we can obtain from the light energy. Okay. So after calculating the reflectivity, then we can calculate the amount of light reflected, which is part A. Okay, so it's 31.5 milliwatt per meter square. Now, which means 69.5, sorry, 60.5, 68.5, sorry, 68.5 milliwatt per meter square of light intensity will be transmitted. Okay. All right. Now we can redo the calculation for 2 eV. Right, for 2 eV, the reflectivity actually is higher, okay, because the photon energy is higher, so more light will get bounced back, okay. Now, for part B, if we want to calculate the amount of light energy absorbed in the semiconductor, we need to make use of Lambert's law. Okay, so after propagating through the silicon for a certain distance, the amount of light energy absorbed can be calculated using Lambert's law. For example, after a distance of 20 micrometer, okay, so you need to use Lambert's law to calculate the remaining light intensity at x equals to 20 micrometer. So the difference between the initial intensity and the remaining amount of light intensity will be the amount of intensity absorbed. Okay, right. So the calculation is shown here. This is alpha, and this is x expressed in terms of meter. Remember, for this example, alpha is given in meter, per meter. Okay, so 64 milliwatt per meter square of light remaining at x equals to 20 micrometer. So the difference between the initial intensity after accounting for reflection and the intensity remaining will give you the intensity of light absorbed in the first 20 micrometer. So this should be micrometer. Okay, right? Now, if the light energy is higher at 2 eV, you can see that the amount of light remaining, amount of light intensity remaining at 20 micrometer is almost zero. It's 0.008 milliwatt per meter square. Okay, so the amount of light absorbed is practically the entire amount. All right, it's about 64.9 milliwatt per meter square. So for the second case involving more energetic photons, most of the light will be absorbed. So no light can escape, or no light can propagate through the semiconductor and escape at the other end of the semiconductor. Okay, all right. Now for part C, so part C is only relevant for the less energetic photon, right? Because for the more energetic photon, all the light will have been absorbed. The light cannot escape back to air again, right? After traveling through the whole semiconductor, none of the light is left. Okay, so only at 1.2 eV, where the absorption is much weaker, then we can still have some amount of light remaining after 300 micrometer, which is the thickness of the silicon wafer. So applying Lambert's law again, you will get the light intensity remaining, right, at the other end of the semiconductor. Okay, so to calculate the amount of light that actually can escape back to air, you need to consider the reflectivity again between silicon and air. Okay, you do not have to calculate this again because we already calculated this earlier. So the transmittivity will be 0.685 times 24.7 will give you the amount of light transmitted back into air. Okay, so this will be the amount of light transmitted back into air. All right, so this is a simple example on the application of the Lambert's law in conjunction with the reflection that always happen between the different media. Okay. All right, so this is a picture trying to describe how the light intensity varies with distance. Now, just caution here, this I refers to light intensity. Don't misinterpret this as the current. All right, this is not current, light intensity. Okay, so initially the intensity is 100 milliwatt. At the surface between air and silicon, okay, at the interface between air and silicon, right, the intensity immediately dropped by about 1/3 due to reflection. And as the light travels into the semiconductor, it can get absorbed. The absorption, the curve shown here is for the 1.2 eV photon energy. So after traveling for 300 micrometer, not drawn to scale, so this is the remaining light intensity. Now, upon hitting the other interface between silicon and air, right, there is another drop of about 1/3 due to reflection. So this is the amount of light transmitted back to air. Now, for the other photon energy 2 eV, the curve would have decayed to almost 0 at x equals to 20 micrometer. All the light is absorbed within the first 20 micrometer layer. Okay. So I think this is a good point to stop. So let's go for a break of 10 minutes and then we'll resume after that. If you have any question, you can ask. I will still be online during the break.
Hi, Professor.
Yeah.
For the absorption coefficient, I noticed that for the like the wavelengths below 0.4 nanometer, there are no data for the absorption coefficient. Why is this so? It's in a diagram.
Okay, let me go back.
Yeah, there's a lower limit for the coefficient.
No, I won't say this lower limit. Of course, we can still go below. 0.4 micrometer actually corresponds to blue light or violet light. So
so it can be extrapolated.
yeah, it can be extrapolated down. There's no reason to stop here. It's just that it so happened that the measurement was stopped here. So this is the only available data at this wavelength. It can also go higher, like for some narrow bandgap semiconductor. These are much narrower bandgap. So the wavelength, the cutoff wavelength for absorption can be higher. So the measurement has to be done at higher values into the infrared range.
Okay, I see. Thank you.
Hi, Prof. Can I ask a question?
Yeah,
I think
sure.
this also pertains to like one of the earlier chapters. So, because you know when the semiconductors dope, right, it introduces like the acceptor and donor level, right?
Yes.
So let's say you shine light, which is below the energy band gap. Will it still be absorbed because of the introduction of the donor and acceptor levels?
Okay, yeah, this is a good question. Now let's consider donors. Okay, so donor levels are very close to the conduction band, right? So basically what happens is that if you shine light slightly below the band gap energy, yes, you can trigger electron hole pair generation, where the electron actually first go from valence band to the donor level and then up again to the conductor. It's possible, yes.
Oh, so like for but then only for intrinsic semiconductors, then it has to be above the energy band gap for generation of electron hole pairs. Okay, thank you.
Okay, just to add on to what you asked, if you look at
Okay.
this diagram again, you know, beyond the cutoff wavelength, there is no absorption. Imagine you have doped silicon. Doped silicon, as you mentioned, you know, they are donors and acceptor level. So that kind of reduce the photon energy needed for electron hole pair generation slightly. So in doped semiconductor, this effect is shown as a small tail. There's a tail. For example, in this case, there's a tail here. All right, this tail could be related to some of the defects present inside this semiconductor. Right, there's a tail in the near the cutoff wavelength.
Okay, thank you.
Thanks.
Hi, Prof. I got a question pertaining to the schedule, actually, not so much to this lecture, but according to the schedule, isn't today's lecture supposed to be on part 4, even though we covered it yesterday? So how would the schedule, covered last week, sorry. So how would the schedule actually change?
Yeah, referring to the lecture schedule?
Yes, yeah, I mean, according to today's 8th Pro and according to the lecture, it's supposed to be effects of bias on Schottky and Ohmic contact, even though we covered it.
Yeah, we already covered that last week. So the lecture progresses now is moving a bit ahead of schedule. One of the reasons, I mean, because in the LT lecture, we tend to talk a bit more. We tend to write something on the board and so on to further explain certain things. So that takes up a bit more time. So for an online lecture, this cannot be easily done. So I cannot write anything so freely for you to see. So that kind of allows the lecture to actually move faster when it is conducted online. So in the past, when we conducted the lecture in the LT, normally the entire part 2 would end during lecture 14, but we didn't use the full lecture 14. We used about 1.5 hours of lecture 14. So for online lectures, most likely we will be able to finish by the end of lecture 13. That means we would have saved about 1.5 hours when compared to when the teaching is done in the LT. Okay, right. So lecture 14 is basically free, so we can still make good use of lecture 14. So one way is to do a revision lecture. Right. Another way is to discuss questions in test 1. All right, I can go through question in test 1, how to solve the 4 questions.
Okay,
and then we can also spend time on Q&A. Yeah.
Okay, thank you, Prof, for the clarification.
Hi, Professor.
Yeah.
I noticed that straight after the test we'll have the exam. So will the test 2 result be released or any like discussion?
Okay, straight after the test, what you are saying is that I think 2 weeks after the test 2, you will take your exam.
Yeah, but we have a study week in between with no lesson.
Oh, okay. Yeah, I think it is possible if most of you are fine. I can actually schedule another online discussion to go through the questions for test 2 during the study week.
Okay.
Yeah.
Thank you.
Okay, I think we can resume the discussion. I guess it's already past 10 minutes. All right, so welcome back and let us continue. So the next discussion will be on recombination. Something which you also already know, right? But there are additional stuff that we want to cover. So what is recombination? Recombination describes the situation where an electron situated in the conduction band falls back and occupy an empty energy state or hole in the valence band. Now, there are different ways by which recombination can happen. Okay. Now, if an electron directly falls from the conduction band to the empty energy state in the valence band, it's called direct recombination. Direct recombination generally is radiative in a sense that it emits light, or the recombination results in the emission of light. Okay. Now, another type of recombination is indirect recombination, and it mostly applies to semiconductors having indirect band gap. Okay, so what that means is that in such semiconductors, electron-hole pair recombination typically occurs through defect states situated inside the band gap. In other words, the electron need to first transit from the conduction band to the defect state before it transit to the empty energy state in the valence band. I will elaborate further on indirect recombination later. Now, there's one point I want to bring to your attention is that before recombination can happen, a process known as thermalization must first occur, especially when the electrons and holes involved are energetic. Now, what are energetic electron and hole? An energetic electron is an electron that possesses excess energy above the thermal equilibrium value. In other words, if you consider thermal equilibrium, most of the electrons are situated very close to EC. All right. So if we apply electric field, the electric field can accelerate the electron, giving it kinetic energy. In that sense, the electron will have excess energy above its thermal equilibrium value. Now, before an energetic electron or hole can recombine, they must thermalize in a sense that the electrons or hole and hole must lose the excess energy through interaction with the phonons, okay, before they can recombine. Or in other words, energetic carriers generally do not recombine so easily. And it's quite easy to understand why energetic carriers do not recombine very easily. Okay. Okay, so yeah, the point that I just mentioned is summarized here. All right, so if electron hole pair exists at energy levels away from the band edges, they are energetic and they do not immediately recombine. Okay, so before recombination can happen, these energetic carriers must go through thermalization. Thermalization is simply a process whereby the energetic carriers lose their excess energy through interaction with phonon. Okay. Now the interaction with the crystal lattice is called phonon scattering. I hope you remember the term phonon scattering. And in the process, the excess energy is transferred to the crystal lattice in the form of a phonon. Okay, right? Just like photon, right? We can think of phonon as packets of energy which are released by energetic carriers. But these packets of energy, they are absorbed by the crystal lattice, the vibrating atoms in the crystal lattice. Okay. So after thermalization, the electron hole pairs at the situated near the edges of the conduction and valence band or band edges will recombine. Okay. So recombination is basically a process where excess carriers are eliminated. So the number of electrons and holes in the semiconductor will decrease with time when recombination happens. Okay. Now, by the principle of conservation of energy, the energy difference when the electron transit from conduction to valence band, the energy difference must be converted into another form. And this can be light and it can be other forms of energy, need not always be light energy. Okay. So the energy release is approximately equal to the band gap energy. Now, why approximately equal and not equal to the band gap energy? Now, this is an important point which might help in your lab session, the lab 3. Okay. If you may recall, this point was actually already discussed in part 1. Now, even under thermal equilibrium, electrons, if you consider the conduction band, electrons in the conduction band, they are distributed over a certain range of energy, right? From EC up into the conduction band, right? Electrons are distributed over a range of energy. Not all are situated at EC. Similarly for holes. Holes are distributed over a certain range of energy in the valence band. Okay, so electron hole pair recombination can happen involving electrons at different energy levels and holes at different energy levels. Okay, so there is not a single photon energy is released. That's the first thing. All right, and the second thing is that the energy released is not the band gap energy. It's approximately equal to the band gap energy. Let me see if I can find a diagram earlier to explain this. Okay, give me a second. All right, I'm back. So I think you should have seen this diagram before in part 1. Okay, I think our interest is on this diagram only. So essentially, how electrons populate the conduction band can be determined by the product of two different functions. One is called the density of state function, which is shown by the black line here. Okay, so as you go into the conduction band, the density of state increases. In other words, you've got more and more available energy states to accommodate the electrons. But on the other hand, the electron occupancy is determined by the Fermi-Dirac function. All right. As you know, Fermi-Dirac function has a value of 0.5 at the Fermi level. And for energy states above the Fermi level, this function goes to 0 very quickly. All right. So if you take the product of these two functions, the end result will be a curve that is shaped like this. Yeah. Okay. So it will tend towards 0 eventually if you go deep into the conduction band, because the probability of finding electron at very high energy level is practically 0. Even though they are available energy states, you don't see electrons there. All right. So the electron concentration actually peak at a certain energy level here. Right. Similarly for the holes, the same concept applies to the holes. Right. The hole occupancy is not only determined by the number of available energy state, but also by the probability. Okay, so the concentration of holes peak somewhere here. Okay, so if you talk about recombination, then electrons and holes at different energy levels can recombine. Right, so for example, electrons here, look at the mouse cursor, can recombine with a hole close to EV. Right, so this will result in photons having a range of energy being emitted rather than one single energy. Okay, right. Now the second point you should take note is that the light having the strongest intensity being emitted does not come from recombination involving electron at EC and hole at EC. In fact, you have very few electrons exactly at EC. In fact, is 0. Right? If you go slightly above EC, there are very few electrons. Likewise, if you go slightly below EV, there are very few holes. So the intensity of the light coming from the recombination involving these carriers is very weak. Okay, so the strongest intensity of light would come from recombination involving electrons situated slightly above EC, somewhere at the peak here where you find many electrons. Similarly, somewhere at the peak here, you find many holes. So when many electrons recombine in many holes, more light is given up. So light intensity due to these recombination events will be the strongest. Okay, right. So we tend to be able to only measure light which have a high intensity accurately. So when we estimate the band gap based on the wavelength of the light that correspond to the largest intensity, it gives us a value which is slightly bigger than the band gap. If we convert the wavelength back to photon energy, the photon energy will be slightly bigger than the band gap energy. Okay, right. So with that, I think that point should become clear. Okay, so it's only approximately equal to the band gap, not exactly equal to the band gap, because there's no way to measure the light emission from electron holes recombining. I mean, from electrons situated exactly at the band gap recombining with holes situated exactly at EC recombining with the hole situated exactly at the EV, since there are very few carriers there. Okay. Now there are two types of recombination. One is radiative or direct. The other one is indirect or non-radiative. Non-radiative means the recombination does not result in the emission of light. Okay, so I've already explained direct and indirect recombination. This is for direct, right? Now, if you take the example of gallium arsenide, which has a band gap of 1.43 eV, right? This means that the photon emitted due to recombination also has energy of around 1.43. Okay, remember gallium arsenide is a direct band gap semiconductor. So in terms of wavelength, All right, this corresponds to 876 nanometer, which is in the infrared part of the electromagnetic spectrum. Okay, so by using semiconductors with different band gap, so we can create light emission having different colors. Okay, this is the basis of how LED function. Basically, if you want a blue LED, we need to choose a semiconductor of the appropriate wave band gap, so that the light emitted will have the correct wavelength corresponding to blue light. All right, so for red LED, similarly, we need to choose a different semiconductor. Okay, I'll come to that later on, right, to probably show you how different semiconductors can give you different colors of light. Now, if a semiconductor has defects, okay, defect states are energy states situated within the band gap. Okay, so when electron falls to these defect states in the band gap before falling to the holes in the valence band, the process is called indirect recombination. Now, in indirect recombination, energy is released in the form of heat, not light. All right, so in fact, in the operation of LED, one objective is to minimize the number of indirect recombination and maximize the number of direct recombination. Okay, right. So for light emission applications such as LED, the semiconductor crystal must be as pure or as perfect as possible, having lowest possible density of defects. Okay, that is to minimize the non-radiative recombination events. Now, the number of defects in the semiconductor is only one of the factors that determine whether the semiconductor is a good emitter of light. There is another more important factor, and this is related to the type of band gap. I think this point was already covered in part 1. So I'm going to go through it quickly. Remember, examples like silicon and germanium, they are indirect band gap. And semiconductors such as gallium arsenide, they are direct band gap. Okay, so the type of band gap can determine whether the semiconductor is a good emitter of light or not. Now, even if we take the hypothetical situation where we have perfectly pure silicon and perfectly pure gallium arsenide, right? No defects. If we have such a scenario, then silicon is still a very poor emitter of light, right? Even though it is perfectly pure compared to gallium arsenide. This is because silicon has an indirect band gap and gallium arsenide has a direct band gap. So how to understand this very quickly, just a recap. So in a direct band gap, right, the minimum of the conduction band coincide with the maximum of the valence band at the same crystal momentum. So during recombination, momentum conservation is not an important consideration. So only energy conservation needs to be fulfilled. Okay, so in this case, the excess electron energy is emitted in the form of light. Now, in the indirect band gap semiconductor, the situation is very different because the minimum of the conduction band and the maximum of the valence band, they occur at different crystal momentum. In other words, for an electron at the conduction band, it has a different momentum compared to the holes at the top of the valence band, right? So in order for this electron in the conduction band to recombine with the holes, its momentum must be changed to a value that is similar to that of the hole. Okay. Now, because an electron cannot change its own momentum by itself, we need a third party, which is called the phonon. Phonon is actually a lattice vibration or a vibrating atom to help the electron change its momentum. Okay. So only when the momentum change is of the correct amount, then electron-hole pair recombination can happen in the indirect band gap semiconductor, such as silicon. Now, due to the interaction between the electron and the vibrating atom, the excess electron energy is converted into heat and not light. So that explains why silicon having an indirect band gap is a very poor emitter of light. Even though it can be very pure, it is still a very poor emitter of light. On the other hand, in the direct band gap semiconductors such as gallium arsenide, if they are defect states, if the defect states is situated at a different crystal momentum, then recombination which happen through defect states would not emit light because the interaction is needed between electron and the vibrating atom to change its momentum to recombine through the defect states. So through this interaction, then the excess energy of the electron is converted into heat. All right. So what I've said is summarized here. Okay, so for direct band gaps such as gallium arsenide, the bottom of the conduction band, the top of the valence band, they occur at the same crystal momentum, right? So in this case, direct recombination leads to the emission of light. In silicon, however, is indirect. So the electron momentum needs to be changed and conservation of momentum has to be obeyed. So there must be a third party that is present to help the electron change its momentum. All right, so due to the interaction, this third party is actually the vibrating atom. So because of that, the excess energy is converted into heat, not light. All right, okay. Right, so momentum change needs to come from the interaction between electrons and the lattice in the form of phonon, which are vibrating atoms. Now, phonon can help electron change its momentum because it has very large momentum. Remember, the vibrating atoms are very big in size, right? So when they vibrate, they have a lot of momentum. Okay, so that can help the electron change its momentum. And if the change is of the correct amount, then recombination can happen. This process involves three particles, electron, hole, and the phonon or the vibrating atom. And because of that, the probability of it occurring is very small. Okay, now, because of that, in the indirect band gap semiconductor, most of the recombination event happen through the defect states. Right, for example, if you have a defect states here, in between the EC here and the EV here, you have a defect state shown by the mouse cursor here. Now, it is much easier for the electron to transit from EC to the defect states because the change in momentum involved is smaller, right, than one big change needed for the recombination to happen. So if you have a defect states here, the electron can transit to here and then transit again to the valence band to recombine with the hole. Now, in each of the transition, the change in the crystal momentum involved is smaller, and it is easier to be fulfilled than one big change in the absence of the defect states. All right, so because of that, recombination events in the indirect band gap semiconductor typically happens through the defect states. All right. Okay, so now at this point, I want to digress a bit. Okay, maybe after this slide. So since direct band gap semiconductor is a good emitter of light, all right, so we can only use direct band gap semiconductor for light emission application involving devices such as the LED light emitting diode and laser. Laser is another kind of PN junction diode. All right, well, since we have time, we can discuss something on laser after lecture, after we finish everything in lecture 13, or we can even do so in lecture 14, okay? Right. Now, here I want to digress a bit. This is not in your slide, but this information could be useful. Right. Now, I want to also briefly talk about OJ recombination. Right. Now, OJ recombination is another kind of recombination event. Besides the direct and indirect recombination, this is the third type of recombination event. Now, what is OJ recombination? OJ recombination involves 3 particles. All right. Typically 2 electrons and a hole. Or of course, it can be 1 electron and 2 holes as well. Okay, all right. Now, it happens like this. So when the electron and hole recombine, the excess energy must be conserved. So in OJ recombination, the excess energy is passed to the second electron here, exciting it deeper into the conduction band. All right, so it goes deeper into the conduction band. In other words, this second electron becomes more energetic because it received the excess energy from this recombination event. Now, this electron eventually will lose the excess energy through thermalization, although it can recombine later on, but the excess energy due to this recombination event is lost. Even if this is a direct recombination event, no light is emitted because the excess energy is transferred to the second electron here. All right, making it energetic, but the second electron will eventually thermalize, losing the excess energy through heat. All right, through interaction with the phonon. Now, since OJ recombination is a 3-particle process, the probability of it happening under normal circumstances is low. And OJ recombination only becomes important when the number of electrons or holes becomes higher, right? Obviously, because when there are more electrons in the conduction band, for example, then OJ recombination has a higher chance of happening. Because of this excess electron, it can always receive the energy from the recombination event, can get excited to become more energetic. Okay, so similarly for the holes. All right, so we didn't discuss OJ recombination because it's not likely to happen under normal circumstances. But let's say if you have a situation where you have excess, many electrons present in the conduction band and many holes present in the valence band due to some external excitation, right, that introduce many excess carriers in the 2 bands, then there's a chance of OJ recombination happening. And even though the recombination event may take place in a direct bandgap semiconductor where light emission is expected, but we may not get light emitting out of the semiconductor due to OJ recombination also taking place. Okay, all right, so just keep that in mind. Okay, now then let's move on to talk about the different kinds of emission besides direct, indirect. Emission can also be classified into 2 different categories, all right, spontaneous and stimulated. So what does spontaneous emission mean? Okay, I think I have a diagram. Okay, so let's look at spontaneous emission. Now, when electrons fall from a higher energy level E2 to a lower energy level E1 in an entirely random manner, all right, it does so on its own at random times, okay, then the resulting photon that is emitted is a result of spontaneous emission. Okay, so since the process of spontaneous recombination happens at random, all right, the photons coming from spontaneous emission is actually also randomly emitted in all different directions. They are incoherent. They have no phase relationship with one another. So the light that comes out as a result of spontaneous recombination or spontaneous emission is incoherent. In other words, they travel in different directions, they are of different phases and so on. Okay, so that is spontaneous emission. So what is stimulated emission? Stimulated emission is referring to the case where the recombination event or the transition from a higher to a lower energy state is triggered by the presence of another photon having the same energy. Okay, So what does that mean? Maybe a diagram can clarify that. So imagine you have two different energy level, E2 and E1, only two. Okay. Now, stimulated emission can happen when a photon of exactly the same energy as E2 minus E1. When this photon is nearby, this photon can trigger the transition of an electron from E2 to E1. All right, so when this happens, this emission is called, the light that is emitted is called stimulated emission. All right, so this transition is called stimulated transition, or if it is involving conduction band and valence band, it's called stimulated recombination. Okay, so stimulated emission, the photon emitted is exactly the same as the photon that triggers, that stimulate the emission. In other words, through stimulated emission, we get many twins produced. All right, all the photons are exactly the same. They are having the same energy. They have the same phase. They travel in the same direction. They have the same state of polarization. In other words, if a particular photon only has electric or magnetic field vibrating in a particular plane, then all photons have the same behavior, right? They all have this electric field or magnetic field vibrating in particular planes only. Okay, so photons emitted due to stimulated emission is coherent. And stimulated emission is the basis for laser operation. All right. Since we have time, I can go a bit more into how stimulated emission can be exploited to produce laser light. As you know, laser is very highly intense. It can travel very long distance without a significant drop in intensity value. All right. So how can that happen? So I can discuss a bit more after we finish this particular chapter. Okay. So with that, I think I will leave LED and photodetector till the next lecture. Right. So we are pretty much done for today. So if there are any questions, I can take them now.
Hi, Prof.
Yeah.
I've got a question about the stimulated emission. Could I clarify how would you electrically force the semiconductor to produce stimulated emission?
Okay, I will come to that eventually, but since you asked, I can briefly discuss this now. In order to have stimulated emission, we must fulfill a condition called population inversion. All right, population inversion, besides having photons of a specific energy nearby. Another condition that must be fulfilled is population inversion. So what does that mean? That means I must have a mechanism by which I place many electrons at a higher energy level compared to a lower energy level. In other words, I have many electrons present at a higher energy level and very few electrons at a lower energy level. This is called population inversion. Now, why people call population inversion? If you remember, under normal circumstances like thermal equilibrium, right, we cannot have population inversion in a sense that electrons always occupy the available lower energy states first before they populate the higher energy states. So under thermal equilibrium, we always find fewer electrons at higher energy level than at lower energy level. But for population inversion, all right, we, of course, through the external excitation, we can create a situation where we have many electrons at higher energy level than at lower energy level. Now, coupled with the presence of photon of that specific energy, then I can stimulate many emission of photons. So that is one way of producing light of very intense intensity, population inversion. And that can be achieved in a PN junction, which I will show you next time. So be a bit more patient.
Oh, okay. So both these conditions need not necessarily be met for the stimulated emission to occur, right? Because for example, in a laser, if we just press the button and close the circuit, then it will emit the laser light. It's not like we have to shine light at the semiconductor component first before it shoots out the laser beam.
Okay, that's a good question. Actually, the photons are a requirement for stimulated emission because that's how stimulated emission works. You need one photon to stimulate the emission of another photon. So your question is where do these photons come from? Okay, all right. To answer this question, remember in a PN junction, if you build a PN junction on a direct band gap semiconductor, and you forward bias the PN junction, you get electron hole injection, and these injected carriers will recombine, and the recombination will produce photons. So the recombination event, they themselves at first can produce photons. But if you design the PN junction diode in such a way that this photon can be trapped inside the PN junction, they can stimulate the emission of more photons. So through this process, you generate lasers. So by pressing a button to close the circuit, you're actually creating many different effects inside the semiconductor. First, you're forward biasing the PN junction, and the forward bias will lead to the emission of photons. And there's a mechanism that traps the photons inside the PN junction diode itself. All right, and by trapping the photons there, you stimulate more photons to be emitted. All right, so it's like a self amplification process. It's a positive feedback cycle that we are trying to encourage here. Okay, so photon produce more photons, and the more photon will produce even more photons, and so on and so forth. All right, so through this process, that's why we can generate laser beam of very high intensity.
Okay, thank you very much.
Yeah, I can discuss this a bit more next time, since we have time now.
Yeah, thank you.
Any other questions?
Hi, Prof. Maybe just one question. I'm not sure that we cover next week, but why do we use a PN junction for an LED? Can't we just use like a gallium arsenide just to without just like a P side or N side gallium arsenide to emit light? Like wouldn't that also emit light? You don't necessarily need to have a PN junction to emit light.
Okay. PN junction is a way to achieve excess carriers on both sides of the semiconductor. Let me go to the diagram of a PN junction. Yeah. You have seen this diagram before. This is a Venn diagram of a PN junction under forward bias. You see, we need recombination to happen. So in order for recombination to happen, we need excess electrons or excess holes. Now, if you only have one semiconductor, not a junction like this, if you only, let's say, have the N type, it is not easy to introduce excess electrons into the N-type semiconductor. You need another material as a source of electron to provide the electron. Okay, so if you do not want to use PN junction, another option is to use a Schottky diode. In other words, a metal. Okay, so a metal can introduce a lot of electrons into a semiconductor. Like, for example, if you form a Schottky diode on a P-type semiconductor, right? You need to introduce electrons into the P-type semiconductor to recombine with the holes. Okay, so a metal can do that. So essentially, a semiconductor, a standalone semiconductor is not that easy to introduce the excess carriers. So a PN junction provide a very convenient mean for us to achieve that through forward biasing.
Okay, I see. Thank you, Prof.
Hello, Professor.
Yep.
May I ask for the recombination in semiconductor? Let's say if we have an electron in high energy state far away from a conduction band, and we have a hole far away from the valence band.
Yeah.
Is there a possibility that these two will directly recombine?
No, these are energetic carriers. So they possess very high thermal velocity or some form of kinetic energy. So they are very energetic. So the chance of them directly recombining is low, is very, very low.
So there is still a possibility, but it's very low.
I would say very, very low. Yeah, very, very low. So even if they recombine, the light emitted is of very, very low intensity.
But what?
It's of not much use. Yeah.
But what energetic particle have lower possibility to recombine?
Okay, you can think of recombining two particles recombining or two particles which are very energetic. What is the chance of them colliding with one another? I'm just using an analogy to explain, right? So imagine you have two particles, they are very energetic. All right, so they zoom past each other almost immediately. Right, so the chance of them colliding is much lower than slower particles, right?
Okay, I see. Thank you. Hello, Professor. I have another question.
Yeah.
May I ask why the electron, when it fall to defect level, the energy will be emitted as heat, not light? Is it because of collision?
Okay, let me go to a diagram to explain that. Okay. Now, let's take the example of a direct band gap semiconductor. Okay, so due to the perfect periodicity of the crystal, right? It is the periodicity of the crystal that generates the band structure. So in the direct band gap semiconductor, the minimum of the conduction band coincides with the top of the valence band. This is due to the periodic structure in the crystal. Okay, so if you have a defect in the crystal, it is like a missing atom, for example. That means there is a change in the local potential function at that particular position in the crystal. All right, so the periodicity there is interrupted. So that will create an energy level inside the band gap. And this energy level is likely to be of a different momentum compared to the EC, the bottom of the EC and the top of the EV. For example, the defect level is here, right? So for the electron to transit to the defect level, it must involve a change in momentum, right? and the change in momentum has to be provided by the vibrating atom. So in the process of transiting to the defect level, the excess energy of the electron is lost as heat, not converted to light. So that's why in the direct bandgap semiconductor, if we want to maximize light emission, we need to minimize the defect density. Right? Now, on the other hand, having defect density in a way is good for indirect bandgap semiconductor because it speeds up the process of recombination. Right? Because if you have defect states in indirect bandgap semiconductor, they provide as intermediate stop for the electron to recombine with the hole. Right? Without the defect states, this is a big jump which has a low chance of happening due to the big change in the crystal momentum, relatively speaking. So if you have a defect state here, the change in the crystal momentum needed is smaller, which can be fulfilled more easily.
Okay, so it means that the this defect will have a fixed momentum, defect energy.
Is determined by the solution of the Schrödinger equation at that particular position. You can solve Schrödinger equation for that particular location, and you can establish the energy versus K relationship for that defect at that position.
But is there a possibility that the defect level situated directly at the below the minimum conduction level energy level?
Here,
yeah,
where the cursor is at.
Yeah.
I would say the chance is almost zero because at the end of the day, you must understand that the band structure is created by the periodicity, the very regular arrangement of atoms in the crystal. Okay, so if you have something abnormal happening at a particular position, such as a missing atom which creates the defect, then the chance of the EK relationship at that particular location having the same as the rest of the crystal is very low, right? Because the local potential function at the position is totally different from the rest of the crystal. So the solution of the Schrödinger equation at the defect location is different. So it is quite low chance that they will have exactly the same crystal momentum, you know, and so on. I would say the probability is low.
Okay.
It may not be zero, of course, but then if the probability is low, then having them around or not having them around doesn't really matter.
Okay. Yeah. Thank you.
Professor, could I ask something about the practical, the lab?
Yes.
So because I missed my first session I missed my lab because I was on MC and I had to get the swab test, so I couldn't go for a lab session. Would there be a makeup?
If you have a valid MC, yes, we will arrange a makeup. I think, did you send me an email yesterday?
Yes, I did.
Oh yeah, you're
Joven.
okay, Joven,
Yeah.
right? Yeah, I didn't have time to reply to the email today. Yes. You would have a chance to do a makeup. It's just that we need to arrange a suitable date and let you know.
Okay, thank you so much.
Okay. Now, guys, for those of you who miss lab 1 because of valid reason, like due to MC or due to some official events, please let us know, okay, so that we can arrange a makeup session for you. There are already a couple of you who have written to us. Just in case there are more. So please let us know if you have missed the first lab, because the lab is gradable and then it will count towards the final grade. The makeup will most likely happen after middle of April. Okay, the reason is because now the lab is also used for undergraduate experiments. So the lab has to cater to the experimental schedule for many undergraduate classes, right? So it's quite busy at the moment. So we can probably, or it will be easier to arrange a makeup after the undergraduate classes are over, which is after next week, right? So we will let you know the date for the makeup very soon.
Hi, Prof. I have a question. So, regarding the defect states, if there was a defect state that had the same momentum as the highest point on the valence band, that has the same momentum as the lowest point on the conduction band, but has the same energy level as the highest point on the valence band, which would the electrons go to the defect state or to the valence band?
So are you referring to a situation like this that I have a defect state here?
No, the defect state would be at the same energy level as the valence band, but the same momentum as the conduction band, like the lowest point on the conduction band.
Oh, okay. So here,
Yeah.
I would say theoretically, yes. Theoretically, yes. If you have such a defect state theoretically, then there is a chance for the electron to fall to this defect state before it goes to the valence band. But I would say having such a defect state would not be very high chance. Theoretically, yes. Theoretically, it is possible. But whether there are many such defect states is another question. So I think probably it's the same as the earlier case. The chance of having such states would be not very high. Right? But if they are, then it's possible, of course.
Okay, then what about the other scenario that you mentioned earlier? So the one where the defect state is at the same same momentum as
the valence. Yeah, it's possible if there is such a defect state here. So theoretically speaking, the electron can come here before it drops to the valence band. So in this case, then the recombination involved in the second step would be direct because there is no momentum conservation needed. So there will be some amount of light emitted. But this amount of light should be weak. Like I say, it's normally very weak because defect states are not many in the first place. And we do not purposely try to create a very defective semiconductor. Although theoretically speaking, in doing so, it promotes the emission of light because you increase the chance of creating all these defect states, right? Like what we have mentioned. But having a defective semiconductor gives another problem or other problems in terms of the electrical performance of the device. So normally we do not go create a very defective semiconductor. You see, the defect density in the semiconductor typically is limited to less than 1%. Right, less than 1%. We do not want it to be very defective. So in that sense, these defect states do not contribute much to light emission, if they even exist, because there are many defect states that can exist. So even if they exist at the correct position, without the need for conservation of momentum, they do not contribute much to the light emission, right? I have another question since we are talking about this. So we talk about direct band gap semiconductor. So recombination will lead to the emission of light. So my question is that in that case, will we see light emission from a piece of semiconductor like gallium arsenide? Because you're told that in a semiconductor, generation and recombination are continuously happening, right? So during generation, the electron and holes are created, and during recombination, they are eliminated. But in a direct bandgap semiconductor, these two processes will cancel each other at thermal equilibrium. But would the recombination in a direct bandgap semiconductor lead to the emission of light? Can we see light? You can think about it. So if you bring a piece of semiconductor and into a dark room, no light source, does it glow?
I don't think it would, because the energy comes from the surrounding heat. So there's no external energy source for which to produce light.
Yeah, so energy conservation must be fulfilled. So if let's say if there is light, then there must be a a conversion of energy. So some other source of energy must be converted into the light. But since there is no external excitation, and if you keep the temperature constant, then that shouldn't happen, right? That shouldn't happen, right? So we can argue that although the thermal generation can create electron hole pairs, during recombination, the photon emitted will be reabsorbed again by the semiconductor to create electron hole pairs. Right. So essentially, there is no excess energy input into the semiconductor. So light cannot be emitted. Okay. Any other questions? Somebody send me a message. Oh, this is the. I think this question is similar to what we just discussed, isn't it? All right. All right. If you have no question, then we'll call it a day here. Okay. So I need to remember to do something before I leave.